Right, so thanks for the introduction and thanks everybody for logging in. I was going to introduce myself, but that was a good enough introduction, I think. Um, this talk is about user interface design for geophysical simulation software written in high-level languages such as Julia and Python. And it's really sharing some insights that myself and my collaborators have gained in our journey writing this kind of software. So this talk is about user interfaces and abstractions. And I'd like to, so I'm going to give you some of my thoughts on that in a general context that could be applied to any geophysical simulation software, but I'm going to try to present these ideas in the context of in the specific context of two pieces of open source software, Oceananigans and Daedalus. So Daedalus is a piece of software written in Python for solving arbitrary partial differential equations using global spectral methods. So it's very flexible because you can type in you can solve any equation that you're able to type in, and the spectral methods they're using are very accurate. Oceananigans, in contrast, is written in Julia. It's almost Oceananigans is written in Julia. It solves specifically the Navier-Stokes equations. We've been working on a couple different flavors of Navier-Stokes equations. The main one is an incompressible model, but there's other models that we're working on as well. He uses finite volume method, and there's an emphasis on ocean applications. So, it implements some complicated nonlinear turbulence closures for large eddy simulation and for general circulation modeling. The numerics are less accurate than Daedalus, but because we're focusing on a particular equation set, we can optimize the code a little bit more, specifically for Navier-Stokes and tracer conservation equations. Also, finite volume method is well suited for complex geometries. And I think I was encouraged to note that both of these codes are almost exclusively written in their respective high-level languages, except for a couple compiled libraries, FFTW, MPI, and CUDA in the case of Oceananigans. So I think there's a lot of talks at this conference that use the word Python in their title. So I think a lot of people appreciate the fact that high-level languages, the power or the importance of high-level languages. But I want to reiterate it, or maybe emphasize why high-level languages are so useful. So what high-level languages do is they provide abstractions that separates humans from hardware. So lower level languages, it's a bit of a squishy term right now, but you can think of a lower level language as something that's catering more to the machine, whereas a higher level language is something that's catering more to humans or scientists. And I guess I think of the ultimate software for geophysical simulation would be one in which the code that one writes to perform a numerical experiment is the same. That is the same document that's used to present it to other people as a paper or in a talk. So that's sort of like the direction I think that we should all be heading in. We're not quite there yet, but it's a good ultimate goal to keep in mind. And so my goal with this talk is to share what we've learned developing software in high-level languages. And in particular, I want to document some patterns that we've observed with the abstractions that could potentially become standard abstractions or standard-ish abstractions in geophysical simulation, and the development of of such a standard or such a knowledge base would help facilitate, you know, new users learning new types of software, different types of software for geophysical simulation, for example, and ultimately just get people thinking about this problem, thinking hard about the problem of user interface design as an important problem. It's not enough just to use a high-level language, but you have to actually solve the design problems presented by these the need to write a user interface. So there's four essential abstractions that I'd like to talk about, or maybe categories of abstractions. And what I'll do is I'll present each of these with code examples in the following slides. And I just want to mention that what these objects are in Python, these would typically be classes. So there would be a domain class. I think actually there was at least one talk where there was a domain class. So you can see there's sort of a convergent evolution occurring with interface design already. In Julia, there are composite types. So Julia doesn't have classes, but it's these composite types play a similar role. And so I'll go through domain, model, simulation, and field abstractions one by one. So the first category of abstraction, which is potentially one of the most important, is an abstraction that represents the geometry. So when we're doing geophysical simulation, we're typically solving three-dimensional problems in a physical region. And so the domain specifies the physical region of the problem that we're being solved. And it also, I'm also grouping in a discretization of the domain, right? So a grid or a mesh. So, you know, a domain might be a rectangle or a spherical shell, and the mesh that discretizes the domain might be a regular rectilinear mesh or a curvilinear mesh. The domain or grid, we call it a grid in Oceananigans. It's a domain in Daedalus. Is typically the first thing that you'll encounter when you're reading a script. So it sets the stage for the script reader, and you know, it sort of tells them the kind of geometry in which this physical problem, this physical experiment is going to be performed. The second category of abstraction that I like to discuss is, in Oceananigans, it's called a model, and in Daedalus, it's called a problem, more or less. The model, it specifies the mathematical model for the physical, the mathematical model that's being solved for this numerical experiment that's being performed. So it specifies a partial differential equation with boundary conditions, maybe some custom interior forcing. And in addition, it may also specify some aspects of the hardware, because the model is where the model also organizes the discrete data that's associated with this numerical solution. So in Oceananigans, for example, so Oceananigans implements flavors of Navier-Stokes equations and tracer conservation equations. So when users construct a model, they're given the options to configure terms in the Navier-Stokes equations. So for example, they can pick the type of Coriolis model they would like to use. Changing this line here will change the Coriolis model. So for example, if you have a rectangular domain that's bounded in a north-south direction, you could change F-plane to beta plane if you wanted to use a beta plane model. Or you can change the turbulence closure to configure diffusion or the closure for large eddy simulation that users are using. A nice, this is just really a side comment, but a nice aspect of using a language like Julia is that users, functions that are defined by users in their scripts can be injected directly into the model without any loss of performance. This is possible in Python too, but you have to do a little more engineering to get that to work. In Julia, it's supported natively. In Daedalus, rather than providing a configurable term, or rather than providing the ability to configure terms in the Navier-Stokes equations, in Daedalus, users type their equations directly into the problem type. And so this is a very flexible method for specifying a model, but one drawback is that it's cumbersome to implement very complicated models, such as those that are used for large eddy simulation or general circulation modeling for ocean applications. So typically users are solving simpler sets of equations in Daedalus. Okay. Okay, so the third abstraction that we think is important is something I'm calling the simulation or the solver. And this abstracts the notion of time integration of the model. So a model represents, or can be thought of as representing, the spatial discretization of the problem, and the simulation represents the integration of the model forward in time. So the nice thing about the simulation is that you can use it. Well, you can, in Daedalus, you can configure your time integration method, and then it provides nice functions for writing a time stepping loop that allow you to inject some interventions or code, plotting code, logging code into that loop. The solver or the simulation manages tasks like computing output and writing it to disk, or other miscellaneous tasks. So, for example, there's a user of Oceananigans who is using the simulation to couple their ocean model to an ice model that's on top of their ocean model. And you know this. So I develop Oceananigans, and the simulation has one of my favorite functions, which is this run bang function. So I just like it when I see run simulation in my script. And down here, there's a little example of what it looks like. So when you call run simulation, then it starts printing this output that we've asked for up here, which is the simulation time. Okay. So the last abstraction that I'd like to discuss is, and I'm actually lumping a few concepts together here, but I think they're related enough that it's warranted, is a field abstraction. So a problem or a model is, it represents the mathematical model that's being solved, and the mathematical model involves some set of prognostic fields and diagnostic fields. So, for example, in the ocean, we typically use, so temperature would be a three-dimensional prognostic field that evolves as the simulation is run. And so it's important, I think it's crucial to have an abstraction that represents a field, like a field such as a prognostic or diagnostic field, and that makes the discrete underlying data visible to users. So the field will have a pointer to an array, for example. In the best case, the field abstraction is also equipped with an infrastructure for constructing analysis tasks. So, for example, in Oceananigans, we're able to use the native arithmetic operators that Julia provides, and we've also defined some calculus operators of our own that allow users to define analysis tasks such as computing turbulent kinetic energy or the X component of vorticity. So these operations are then wrapped into what we call a computed field, and then as the simulation is run, the computations can be asked for and then output to disk. So this allows, this avoids the one common problem, which is that software for general circulation modeling typically requires a lot of the developers are tasked with writing a lot of diagnostics themselves, which is not only cumbersome for developers and can be difficult to maintain, but also limits what users are able to do. So by providing this infrastructure, we allow users to define their own diagnostics. Daedalus has something similar, except that rather than constructing these objects directly from fields, users typically use strings. So similar to the way that equations are specified, output tasks are specified using strings, but under the hood, it's working almost the same way as Oceananigans, in that fields can interact and expressions can be stored and then lazily computed on demand. It's important to note, I guess, that in addition to allowing this sort of abstract definition of computations, it's also, of course, possible to handwrite kernels or pieces of code to compute diagnostics if that's necessary, maybe for performance reasons or because the notion cannot be expressed with the abstractions that are provided. And then linked to the whole field infrastructure is some kind of abstraction that writes output to disk. So in Oceananigans, we have output writers, and we support a few different output types. And in Daedalus, it's called a file handler, and you can see it's functioning almost the same way. We have a schedule here for Oceananigans, but in Daedalus, it's called the simulation time step at which the output is performed. Okay, so now this is my last slide. So I think hopefully the main point that I'm impressing listeners with is that user interfaces are important because really what, we're writing software so that scientists can produce knowledge, and a good user interface will make scientists more productive, minimize time to science, and result in more knowledge creation. So it's a win for everybody. User interfaces, it could seem like a trivial point, but it's crucial that the user interface makes model properties and data visible to users, so that, especially in high-level languages, which can be used interactively, having visible data that users can play around with interactively, work with, and plot easily is crucial for making software easy to use, because that's a primary way that users learn software. I think we typically recommend that people, when they're developing a numerical experiment, they start on their laptop and they develop it in a simple context that allows them to rapidly prototype and develop their experiment, even if at the end of the day, they're still going to crank up the resolution and run it on the supercomputer. That prototyping phase is crucial and often where the scientists spend most of their time. Good user interface, it can help produce readable, self-documenting scripts and thus further the cause of reproducible science. So as I said, my dream would be that a paper and a script are actually the same thing. And reading a piece of code, it looks like reading a LaTeX document, for example. I guess I have this parenthetical point at the end, just that when you write your software almost exclusively in a high-level language, it really facilitates the process of developing user interface. It's not necessary. All these concepts apply to writing wrappers in addition to writing software that's top to bottom in a high-level language. But if you do write your software top to bottom in a high-level language, it's fun and very productive for developers as well. So there's a script. A lot of the snippets that I was presenting come from Oceananigans and Daedalus scripts that are at this GitHub address here. And below, I just have two visualizations. The visualization on the right is from Oceananigans, and it's very similar to the script that I presented. Although users would still have to go to somewhere. I didn't write the visualization into this script on GitHub, unfortunately. And then on the visualization on the left is Daedalus in a spherical geometry, a slightly different problem. Okay, thank you.